Well, I think there's a typo in the title as it appears in the program, probably my fault. But anyway, that inspired me to include this alternative title in an old-fashioned kind of way. What's so special about this Faro North site? I'm sure there are young people who hear this term often and are puzzled a little bit about why it's such a widespread notion that the earliest crust was this Faro North site. And I think that there are probably many of the cognoscenti who don't quite appreciate the implications for the bulk composition of the moon that follow from the distinctive characteristics of the Faro North sites. Well, I don't think it's any coincidence that just as soon as samples were acquired, the notion of a magma ocean was put forward by John Wood and his co-workers. A globe-spanning deep layer of magma floating up buoyant plagioclase to form the earliest lunar crust. Now, we shouldn't fault John Wood too much. He wasn't perfect, but he included in the arguments for this model. He realized that this would be a cumulate mechanism. You're floating up plagioclase, and he imagined that he saw in Apollo 11 tiny little fragments that he had. These were Mara soil sample with little fragments from the highlands. He imagined that he could see cumulate textures in this, for example. Now, today, I don't think anyone would call that a pristine cumulate rock from the highlands. This is an impact melt, a poikilotic type of impact melt. And I think that what Wood really appreciated sooner than anyone else, and what to my mind is still the single best argument for this notion of a massive magma ocean on the primordial moon, is that melting to produce basalts and having piecemeal emplacement of magmas near the surface of the moon. Basalts will always be, will always form along cotectics such as this here. This is one example of a phase diagram. And so it'll have roughly equal proportions of plagioclase and mafic silicate. And so any amalgamation of basalts or intrusive equivalent gabbro will leave you with a roughly gabbroic composition. And what we see instead is this an orthositic composition, 26 or so percent Al2O3, 3/4 roughly plagioclase feldspar. And another line of argument that came along pretty early was from the analyses of Mara basalts. People saw that Mara basalts, whoops, I keep pressing the wrong button. Mara basalts pretty consistently have negative europium anomalies. And the highland crust is complementary, as epitomized by Faro North side here, with large positive anomalies. And so that ties in nicely. But the key thing that makes this an argument for a magma ocean is that these Mara basalts are almost without exception far from saturation with plagioclase. They left behind mantle regions devoid of plagioclase, just with mafic silicates, maybe some spinel oxides, ilmenite or something. So there was no plagioclase holding down the europium to produce the negative anomalies during the proximal melting that produced the Mara basalts. It has to be traced back to some process that worked over a huge fraction of the volume of the lunar mantle. And so that tends to call for something like a magma ocean. So I've mentioned, in my view, two of the four most compelling, persuasive, significant arguments for this concept of a magma ocean. To go further, though, we have to start to think about pristine highland or non-Mara rocks. And what we mean by that is rocks that survived with compositions from igneous processes, as opposed to what's so prevalent in the highlands is impacts have jumbled all the materials. If they haven't melted them, they've just mixed them physically to produce polyimide breccias. And so it's a small subset of all the hyaline materials that preserve at least compositions that are from igneous products. And it's even rarer for them to be texturally pristine. And the other argument that I consider important, but I don't have time to address, it would be a whole talk, is in detail, but it's simple, basically simple, is that many pristine rocks, one of the arguments is that many pristine rocks, especially ferronorsites, have very ancient ages. This can be complicated. There was mention today of 6025, shows a somewhat younger age than that. 6025, as Odette James showed years ago, is not quite what we would call pristine. It seems to have mixed together to a limited extent. It's a rare case where it's not quite what we would call a pristine rock. So it's not too surprising that it would have yielded a somewhat younger age. What I want to talk about mainly is the distinctive geochemistry of the ferronorsites, bimodality, compositional bimodality among the pristine rocks. Now this is an example of what is not a pristine textured rock. The first thing we look for when we try to identify these pristine rocks is a texture in thin sections. And this is an impact melt, fine-grained. And if you notice, there are areas that are poikilotic, like that sample that I showed earlier from the Seminole Wood et al. Paper. This is a texture that is pretty persuasively pristine. It's very coarse-grained. It was recognized as soon as astronauts picked it up that it's something very special. It was dubbed the Genesis rock. Very coarse-grained, and it does have, as we'll talk about, a distinctive chemistry too. It's a ferroin and orthosite. This is kind of more representative of some of the best cases of surviving pristine textures. You can see a coarse, and I don't know how well it shows here, but it's somewhat clear that it's a cumulate texture of the original rock, these coarse orthopyroxenes and plagioclase. Even in this case, though, you see shock melt pockets within it, reminiscent of the things that we see in some of the shirkatites. So even here, the texture is far from pristine, but we think that this is a compositionally pristine rock. This is another example of a relatively compelling, pristine texture. It's not as coarse-grained, perhaps, as you would ideally want to see, but the plagioclase here is poikilotic on a much coarser scale than the impact melts texture that is otherwise analogous. This is an impact melt breccia. Clive Neal talked about this morning. 14310. It was one of the ones that was an impact melt that was a little hard to recognize as such for a while, and there was some debate about it. People measured trace elements that made that pretty clear, but also it turned out that there is this one exotic class suspended in the material. So it's today not much disputed. This is an impact melt. But I mention this in part because to acknowledge that texture is not sufficient to, in and of itself, always spot pristine samples from, distinguish them from non-pristine samples, because in principle there will be fine-grained volcanic pristine samples. It's one problem. So aside from textural evidence, which is always the first and foremost thing we want to look at, we can turn to other lines of evidence to try to make this distinction. And very widely relied upon then would be trace siderophile elements. Siderophile meaning iron metal loving. Iron loving, but what we really mean is iron metal loving. These are elements that track with metal, and as such, most of the impactors that did all this impact damage to the earliest crust contained metal and with it siderophile elements. And if they didn't, they'd still impact it through a megaregolith, which has about 2% of chondritic material in it. So it's hard to do this jumbling without incorporating highly siderophile elements. So we can use that as a neat tool, and this is an example of that. We had a sample relatively late in the game from Apollo 14. Its texture wasn't so clear-cut because it's relatively fine-grained. It could be an extrusive. It may be a shallow intrusive. But it wasn't bret shaded, so the texture gave a lot of hope. When we measured siderophile elements, that made it pretty clear that it's not a polyimic breccia or an impact melt breccia, whatever similar distribution what you see here with polyimic breccia. So texture, siderophile elements. Another thing we can look at is the mineralogy. And now I show this as an example. Greg Snyder studied these rocks, and this is the case, I don't mean to pick on Greg, but this is the case where I think he was not sufficiently conservative. He assigned to these rocks classification as intrusive or even plutonic. But if you look at the grain sizes, they're really quite fine-grained. The criterion we talked about was 3 millimeters. That you had to have some grains at least close to that. These grains are mostly much less than a millimeter. But I mention these samples also because even without looking at the texture, somebody telling me that these are intrusive or plutonic rocks, I would be very skeptical just based on the mineralogy, because these pyroxene compositions are very poorly equilibrated. This is indicative of rapid cooling very near the surface. Or perhaps not so near the surface, but an impact melt quenched by cold plastic material. So these are much more likely, in my opinion, impact melts. So it's just to say, it's not cut and dried as we'd like it to be, identifying these pristine rocks. But there is broad agreement about some of the ones that are pretty obvious. And in the 70s, people started to notice that when you look at the chemistry of the rocks that are pristine, or plutonic is a near synonym for that. This is from Jeff Wanna et al., and even earlier Eric Dowdy noticed, he was the first to notice how distinctive. The anorthositic samples turn out to have distinctive compositions. And what's distinctive about them is in comparison to other geochemical attributes, especially involving elements that concentrate into plagioclase, we call these plagiophile elements, they stand out as being unusually poor in magnesium, rich in iron, ferroin. That was data for minerals. Here, this is bulk rock data, but it amounts to practically the same thing, because the bulk rock magnesium and iron is contributed by just a phase or two, pyroxene and or olivine in these cumulate rocks. And these elements, just like calcium and sodium, which I showed on the previous diagram, these elements are concentrated into plagioclase, or plagiophile elements. And europium, like sodium, is a little less so tending to concentrate as is aluminum. So you see these ferroin samples standing out there already. Gosh, okay. It turns out besides this distinctive geochemistry, they have a systematically higher proportions of this phase feldspar that imparts buoyancy to these rocks that formed the earliest lunar crust, we think. And the other samples, which are mostly what we would call magnesium sweet, Mg sweet, they don't have that. These would have sunk onto the floors of whatever magma chamber they formed in. These floated. All right, I'm going to skip this pretty much. There's always been a concern about heat source, and this was partly the early motivation for saying that maybe the Magma Ocean wasn't what happened. The giant impact model alleviated most of these concerns, but it partly motivated by concerns about heat sources. People have always thought about alternative models. And the one that's most widely cited, I think justly so, is mainly the work of Longhi and Ashpal. And what they proposed is that we had no magma ocean. Instead, a lot of small intrusions were in place toward the surface of the moon, and then diapirs, mushes, mostly solid, rose up buoyantly and formed this relatively pure plagioclase layer at the lunar crust. I don't think that model really works as well as the Magma Ocean model, and one of the reasons is that the textures, I showed you 1415, it has an annealed texture as this model predicts. It's not as sheared as I would expect. There's no evidence for shearing in 15415. But most of these rocks have vestigial cumulative textures. This may be the best example. It's not, there are only a few candidates, and most of them don't have very much mafic silicate in them, as the slide previously just showed. But where we do see it, this looks like a pretty good example of a cumulative texture. Okay, what was the mechanism that produced this? Well, this paper here is one of the ones, if I could do over the writing of a paper, this would be at the top of my list. When I wrote this, I thought, wow, people will be citing this galore because this is really great stuff. But I got kind of sidetracked with this notion of an orthocyte assimilation, which is a valid concept, I do believe. But it presented this, what is really the important thing, kind of got lost. And I want to talk about that now. This is the mechanism that I believe produced this spheroid composition. Now, we can imagine, these are two contrasting scenarios. If you have a small amounts of melting in a conventional style, and place that towards the surface of a body, it will form from with a cotectic kind of composition, or close to it at least. And so it'll be, if not immediately, it'll be quickly reach saturation with feldspar as well as mafic silicates. So when you have both of them fractionating, then both of these ratios fractionate together and you have a diagonal trend. But the magma ocean, uniquely, the magma ocean was a circumstance where you had extremely high, whoops, I knew I'd do that, where you had an extreme high degree melting. And so you started out with an ultramafic composition. In that case, you do a lot of crystallization of strictly mafic silicates before any plagioclase begins to crystallize. And in that long stage of strictly mafic silicate crystallization, you go pretty much horizontally on this kind of a diagram. And so you drive the composition of the melt and consequently of the crystals in this direction. Now, eventually you reach plagioclase saturation, you go along diagonally, and this is how I believe the ferro and orthocite suite got its distinctive chemistry. One could imagine a scenario where the magma ocean wasn't so deep, it wasn't such a high, extreme high degree melt of the lunar interior. Or one could imagine that the moon was endowed with a lot of aluminum and calcium. In that case, even if you did melt it to an extreme extent, you wouldn't have such an extensive phase of crystallization of solely mafic silicates. And you could imagine a range of scenarios. But the difference among these is, to get here, you have to have a very extensive melt on the primordial moon, so that you have extreme ultramafic starting composition. And you can't do that either unless you have an Earth-like bulk moon composition, as opposed to, there's a lot of thought that the moon is very appreciably enriched in the plagioclase forming elements, aluminum and calcium, and other refractory elements in the cosmochemical sense. And I don't subscribe to those. This is gratuitous to wake you up. This is just one of these beautiful images from LRO, and because I wanted to mention Mara basalt. I know I'm running low on time, but among the Mara volcanic products, there are, of course, two fundamentally different classes. And this is, to my view, the best argument that the melting, although I just showed you how extensive I thought it was, I don't think that's the whole moon or anything close to the whole moon was melted. I think that the moon has just got this Earth's mantle-like composition, and you had extensive melting, but not close to whole moon, because we have the Mara pyroclastics were lofted out, of course, by volatiles that were in the initial magmas. And probably graphite was involved. Graphite has a density of 2. It would have very efficiently been lost to the deep interior of the moon in any involvement in a magma ocean. And notice that there's the pyroclasts that are associated with primitive compositions. These primitive zones retain volatiles. And I'm not going to try to put a number today for you. Sure, I don't have time if I wanted to. On the what I think is the bulk composition of the moon. I'm not going to play that game, but just I think there's no reason to think that it's much different from the mantle of the Earth. And the isotopic evidence is piling up in that direction. You see this enormous diversity among planetary materials as a whole. The Earth and Moon practically indistinguishable for these isotopes. Epsilon 50 has just recently been added to that story. And so I'm going to have to skip this stuff, sorry. Conclusions, most of the evidence not only favors a magma ocean, but one that was very extensively large fraction of the lunar volume, depending on the bulk moon content of these plagioclase forming oxides, alumina and calcium. Survival of the volatiles points, on the other hand, towards an appreciable fraction of the interior that escaped involved in the magma ocean, retained volatiles, or even in a magnosphere, I should say. And another gratuitous LRO image. Thank you very much.
Okay, we had time for one quick question. Yes, sir, in the back.
David Green, hi Paul. If we actually got to go back to the moon and collect a sample that would, in your mind, be the best one to test the lunar magma ocean hypothesis, where would you like to land?
Wow, that's a great question. I haven't thought about that. You know, I've been working on South Pole Aiken, and that was not the goal. The goal was to test the Nice model and all that stuff. The one place, man, you got me. I'm embarrassed. You know, you'd want to go near a big basin. Again, I still think you might want to go to South Pole Aiken because that is the biggest basin, and the basins are so key to the whole story of how you interpret all the highlands. So I still think I would want to go to South Pole Aiken, maybe not to the interior where we want to go to be sure we get the impact melt and constrain the impact history. I might want to go toward a big basin towards the outside of South Pole Aiken for that particular purpose.